Okay, so let us continue our solutions now with exercise 4. In this one, we are given two integers a and b that are relatively prime. We then have to prove these things, these four other statements. So in the first part, A, we need to prove that if this is the case, then the GCD of a plus b and a minus b is 1 or 2. In fact, hint is also given. We have to somehow show that if we are denoting this GCD by D, we have to show that D divides both 2a and 2b, and then we can apply some things like this. So let's see what we can do. So we start off what is given in the hint. Let D be the greatest common divisor of a plus b and a minus b. Then, being the GCD of two integers, by definition D divides both of them. So D divides a plus b and D divides a minus b. Then from these two divisibility relations, we are now going to show that D divides 2a and 2b, which I think you can already see how to do that. Because D divides these two integers, so D would divide both their sum as well as their difference. Thus, D divides a plus b plus a minus b, which is equal to 2a, and D also divides a plus b minus a minus b, which is 2b. Now D becomes a common divisor of 2a and 2b. So by the definition of GCD, D would divide the greatest common divisor of 2a and 2b. This implies D divides. I know something else is given there in the hint. The hint actually asks us to use the fact that D is less than or equal to the GCD of 2a and 2b, but let's just use this one. GCD, I don't have space here, let me continue from here, 2a and 2b, and from a previous result on GCDs, because 2 is common to both these integers 2a and 2b, and 2 is positive, so we can take 2 common out and we will be left with this, which is of course 2 because GCD of a and b is 1. So that means D divides 2. Now note that D being the GCD of some integers is actually by definition a positive integer. So that means D is a positive integer that divides 2. So there are only two possibilities. D will either be equal to 1 or it will be equal to 2. Since we mention the positivity of D, since D is greater than 0, which is coming from the definition of GCD and D being a GCD, since this is greater than 0, we have d equal to 1 or d equal to 2, and that's what we wanted to show. Okay, so that is part A. Part B, for the sake of distinguishing these different GCDs, let's just call this D1. If you want, in the next one also you may choose to call this one D, but it looks a little strange because it's the same solution. No? Different parts of course, but still. So we are going to name them differently. D1, D1, D1. Okay, so now part B. Let D2 be the GCD of 2A plus B and A plus 2B. There is one subtle thing that I have not mentioned here in part A, and in fact that same thing is there in the other parts also. See, GCD exists only when the integers of which we are taking the GCD are not both 0. Okay, so the hypothesis that A and B are relatively prime, that is, that their GCD is equal to 1, has in itself this condition that either A is non-zero or B is non-zero or both are non-zero. From that, actually one has to conclude that A plus B and B plus C cannot be simultaneously 0 in order to be able to write like this, because if it turns out that A plus B and A minus B are both 0, then GCD does not exist. But that part I leave to you. Okay, it's a very subtle thing which one may not see at first, but it is there. It should be included actually in the solution itself, but I am choosing not to do that. I am leaving that part to you. In most of the cases that is almost evident, but for some cases like this it may not be that evident, it may not be that obvious. So that part is left to you. To show that in the beginning itself, the GCD that you are considering, the ones that are we have to show this is this, that is that, those GCDs exist in the first place. So leaving that to you, now I am just simply writing let D2 be the GCD of these two things. Then D2 divides 2A plus B and just like before, D2 divides A plus 2B, and what is it that we have to prove in this case? That the GCD is either 1 or 3. Hence, here also we are going to take well, we won't shall we take sum? Sum actually will not give us anything useful here. Let's see what we can do. We somehow have to bring 3. Like in part A we brought 2, so here somehow we have to bring 3. For that, simple sum or difference will not work. Something else has to be done. Hence, okay, so how to, for example, bring 3A, can we do that? Yes, of course we can do that. See, like this. Hence, D2, do I already need ink? No. 2 times, let me do this. 2 times 2a plus b minus a plus 2b. So that 2b and minus 2b will cancel out, and 4a minus a will give us 3a. And just like that, if we do the opposite, 2 times a plus 2b minus 2a plus b, then what shall we get? This time 2a minus 2a will cancel out, and 4b minus b gives us 3b. So just like before, D2 now is a common divisor of 3a and 3b. So it will divide the greatest common divisor of 3a and 3b. This implies let me write here. Which implies D2 divides, all the steps are like before, and this in turn implies D2 divides 3. Since D2 is, being a GCD, a positive integer, the above divisibility relation implies that D2 is either 1 or 3, and that's what we needed to show. Okay, then we move on to part C. In part C, we have the numbers that are involved are a plus b and a square plus b square, and we need to prove that their GCD is either 1 or 2, like part A. So let D3 in this case, that thing that I was talking about a while back, that you need to first of all show that the numbers, the integers involved, at least one of them is non-zero. In this particular case, that is rather easy to show. That is because you see, your hypothesis is this, no? A and B are relatively prime. That just simply means that either A or B is non-zero or both are non-zero. So just forget about a plus b, you concentrate on this a square plus b square, that cannot be 0, because for this to be 0, both a and b have to be equal to 0, which is not the case. So this will be non-zero. So in this case, D3 exists, and we can see that immediately, almost immediately. Yeah, I think now I need a little ink. Okay, now in this case also there is a hint, and the hint gives us this identity that a square plus b square equals a plus b times a minus b plus 2b square. So let's just use that. But before that, of course, we have to write this immediate conclusion. Then d3 divides a plus b, and d3 divides a squared plus b squared. So d3 divides a squared plus b squared minus a plus b times a minus b, which equals, this will be a squared minus b squared, that means minus a squared plus b squared, so we get 2b squared. Okay, but then what? Now d3 divides 2b squared. Okay. This implies, now we are going to again use this one and this new divisibility relation that we have derived. This implies d3 divides 2 times a squared plus b squared minus 2b squared, and that equals 2a squared. This part that d3 divides this is coming from here, and this one, of course, we have already proved it. So now d3 divides both 2a squared and 2b squared. Thus it would divide the greatest common divisor of 2a squared and 2b squared, which is equal to 2 times, like before, GCD of a squared and b squared, and that is equal to 2. But we need to justify how it is equal to 2. That means we have used the fact that this GCD is 1, but it's not given that this GCD is 1. What is given is this. This is our hypothesis. Now, does it follow from this that this is also equal to 1? Yes, but how? Actually, this is a part of an exercise we have already solved before. So, we are now going to mention that. Note that by exercise, what is the number here? These things I am never able to remember. 20F of section, that also we need to mention. Now 20F of which section? The previous one. We have this. In fact, this part F of this exercise asks us to show precisely this, that if a and b are relatively prime, then so are a square and b square. So that's what we have used here. So now d3 divides 2, and like before, since d3 is positive, so we have d3 either equal to 1 or equal to 2. or T3 equal to 2, and that completes part C. Now finally we come to part D, and in this case we are to show that the greatest common divisor of a plus b and a square minus ab plus b squared is either 1 or 3. So we start by naming this GCD a plus b, and it looks weird to write it this way. Okay, so this is our D4. Then D4 divides a plus b, and D4 divides a square minus ab plus b square. Hence, here also we have a hint in which an identity is given. Namely, this expression equals a plus b whole squared minus 3ab. So we are going to use that. So D4 is going to divide this. Okay, so exactly how are we? Yes, because you see what is given is this: a squared minus ab plus b squared equals a plus b whole squared minus 3ab, which is equivalent to this 3ab equals this minus this expression. Okay, so here we are going to write that. And this follows from these two divisibility relations, which you can clearly see. Because D4 divides a plus b, it will also naturally divide its square, and this, of course, we just have simply used this, the second one. And this thing equals 3ab. There are some things which perhaps I should mention here. You see, using this type of symbols somewhat casually can lead to some types of confusions. You see, although from the context we can figure out what the thing ultimately means, but still I am saying, you see, here what we have written is D4 divides this, and then we are continuing with this equality equal to 3ab. What that simply means is that D4 divides this expression, which is also 3ab. It does not mean that this relation, that D4 divides this, is equal to 3ab. That, of course, it does not mean, but still sometimes we may get confused. So you have to properly understand from the context what the meaning is. Okay, so now D4 divides 3ab. Now what can we possibly do from here? It may not be immediately apparent what is to be done. So let's just see what we can do. So now next what we are going to do is we are going to use this divisibility, that D4 divides a plus b, and this one, that D4 divides 3ab. And what we can do from here is this. Thus d4 divides 3 times, well, not just simply 3 times, but 3a times a plus b minus 3ab. So that thing that I was saying here just now, I said that these symbols can lead to some confusion. That confusion in fact will be, if you really get confused with these things, here it will be even more, because there is a line break. So ideally I should write minus 3ab, I mean in the same line, but of course I don't have space, so you have to understand what we are writing here. And that thing is equal to what? 3a square plus 3ab, 3ab minus 3ab will cancel out, so we are left with 3a squared. So d4 divides 3a squared, and d4, let me just make it somewhat more confusing. I am now going to continue from here, so you have to understand that it just is a continuation. d4 divides, the other thing that we can do is this, 3b times a plus b minus 3ab. So that again a 3ab is cancelling out with minus 3ab, but now we are left with 3b square. And you of course understand where these two things are coming from. We are using this thing, that d4 divides a plus b, so a part of this expression is divisible by d4, and the other part is 3ab is of course divisible by d4, that we have shown here. Okay, now now combining these two things, now I think you can see what is to be done next. Now it's very easy, because we have got 3a square and 3b square, so we can now just simply take their GCD, and that will be divisible by d4. We were having quite dry days here, dry and hot days, but today it rained in the afternoon, which actually has not helped us. In fact, it made things worse. Now it is dry as well as humid, so that's why I cannot clean it properly. This implies d4 divides the GCD of 3a square, where is that? 3a square and 3b square. Which implies d4 divides 3 times the GCD of a square and b square, and this is again going to be 1. Now you know, because we have already used it once more. Divides 3 by, let's just again mention that, by exercise 20F of section, is it 3? No, it's 2, because we are still in the second chapter. Thus, so now again like before, since d4 is greater than 0, this is either equal to 1 or it is equal to 3, and this completes the solution. Next, exercise 5 for positive integers Nowadays, whenever it rains, it is actually more of a problem. The one thing is that the temperature has gone up, not just here, in fact throughout the world it has gone up. There is a sudden change. Now the problem we face here is that the rain never just is a rain anymore. It always comes with thunders, lightning, and there will be a storm before the rain. So when this happens, we have power cut, and then the power is not there for a long time. So that is a problem. And the other problem is that because we have because the temperature has risen, so instead of feeling somewhat cool, the heat continues to be there, and since the humidity also rises, we are constantly sweating, and it's very difficult and disgusting, in fact. For positive integers, a and b, and n greater than or equal to 1, show the following. Well, the author could have just simply said for positive integers a, b and n, because n greater than or equal to 1 means it's also a positive integer. But anyway, part A, if like before a and b are relatively prime, then the GCD of a to the power n and b to the power n is also equal to 1. Hint: see exercise. So this exercise that we have been using in these parts, now we have to see that one, because you can see that this is the generalization of that exercise. Okay, and there is a part B, the relation a to the power n dividing b to the power n implies that a divides b. Okay, note that the hypothesis that a and b are relatively prime is only in part A. In part B, that hypothesis is not there. We may easily forget this. And here also a hint is given. In fact, in the hint, the entire solution itself has been given. Put D equal to the GCD of A and B. So we may forget that now it is not equal to 1. So we may have a tendency to just simply assume that this is D is equal to 1, but that is not the case here. And write because D divides both A and B, so A and B are multiples of D, integer multiples. So say A is RD and B is SD, where R and S are integers, and from our previous results on GCD, we already know that these integers R and S themselves are relatively prime. That is, the GCD of R and S is equal to 1. More simply put, A and B are any two integers and their GCD is D. Now if you take D out of A and B, then whatever is left, R and S, they will be relatively prime because you are taking all the common factors other than 1 and you are just robbing A and B of common factors other than 1. So whatever is left, they are going to be relatively prime. Where, so that's the thing now we will mention, where GCD of R and S is equal to 1. By part A, GCD of R to the power n, the nth powers also are relatively prime. Show that this R is equal to 1, whence from where we have that A is equal to D. Okay, so let's now see the solution. In part A, actually we don't have to do almost anything. I'm now going to write something like this, and I in fact won't say also what, I won't explain what these things mean. I leave that to you, because what we are now going to write here is about this exercise itself, which we have already come across. We solved it and the solution is available, so it's your task to go back to that and figure out what we are going to write here. Using exercise 20F of, no, it is not F, I think I wrote it incorrectly here, because no, it is not F, yeah, here also it is, yeah, now I am remembering, it's not part F but part A actually. You will realize, you go back to this exercise and why it is part A, that also you will realize. Of section 2.2 and induction. We have this thing, GCD of A and B to the power n is equal to 1 for all positive integers n. So, in a similar manner, we get again by that part of that exercise and induction this next thing. Of course, I am not saying many things here, I left out, so that I leave to you to understand why this is a solution to part A. Now we move to part B. In part B, let's just first of all blindly follow what has been written here. Let, and then we will see how we can use these things. Let D be the GCD of A and B. Then there exist integers R and S such that the hint, of course, that's what we are writing here or using, but we are making the language a little bit more elaborate. We are going to say that the existence of R and S comes as a consequence of this itself. That's just it. Such that A is equal to RD, B equal to SD, and R and S are relatively prime. And this last bit is of course coming from a previous result. So by part A, because R and S are relatively prime, so will their nth powers but now let's just remember what we have to do here. We have to show that if A to the power n divides B to the power n, then A divides B. So let us now start with this hypothesis. Now, if divides B to the power n, then B to the power n is equal to, say, T A to the power n for some integer t. That's what this divisibility relation means. For some integer t, okay, then now in this equation we are going to use these expressions for A and B. So since B is SD, so we get S to the power n times D to the power n equals T times A is RD, which implies T to the power n is equal to T times R to the power, oh no, sorry, what am I writing? S to the power n equals to T times R to the power n. By the way, how am I cancelling out this D to the power n? I can of course do that provided it is non-zero, and it is non-zero. Why is that so? Because you see, D is after all a GCD, and GCD by definition is positive, so it can never be zero. So from that we are getting this. But what does this imply? This in turn implies that r to the power n divides s to the power n, and hence the GCD of r, let me just use this also a part of this argument. This thing we already have. Okay, we have concluded and we now have this thing at our disposal. And this divisibility relation then implies that because r to the power n divides s to the power n, it's in fact is equal to the GCD. Thus, now if r to the power n is equal to 1, there is one more subtle thing here, and that thing, however, now only I see that. How can I conclude from just this that r is equal to 1 though? I can conclude that r is equal to 1 from here itself, provided r is a positive integer, that is r is not negative. That, however, will not just simply come from what is given. Why do I say that? That is because a and b are just some integers. We have not said anything about them being positive. So that is a problem. Now, can we rectify that problem? I mean, if we are following the hint and we have done all these things that have been mentioned in the hint, then we get here, and now from here we can conclude that r is equal to 1 only when r is positive. If r is negative, what goes wrong? Let me just see actually exactly how are we going to conclude it? Say r is positive, then from this how does it follow that r is equal to 1? This equation is equivalent to this, r to the power n minus 1 equals 0, and if you recall, there is an identity in elementary algebra which looks like this. Now, if r is positive, then this thing is also strictly positive, because you see we don't have any minus here. All we have are powers of r, and we are taking their sum up to the n minus 1th power starting from 1. So this thing will be positive. So the product being equal to 0 would then imply that this has to be equal to 0. There is no chance of this ever becoming 0 if r is positive. So from that we will be able to conclude that r is equal to 1. But if r is negative, things will become very complicated, and in particular, you see, we of course have not said also anything about n other than the fact that it is a positive integer. If n is even, positive but even, then you have the option of taking r equal to minus 1, no? Because then r to the power n is still equal to 1, but r is not equal to 1. Now, whether r is, from this we can of course conclude that r is either plus 1 or minus 1. Now, where is this thing taking us? That is the important thing. If R is plus 1 or minus 1, that means A is plus D or minus D, as opposed to A being just equal to D, as we have in the hint. Now, if A is plus D or minus D, okay, yeah, okay. The solution, there won't be any problem with the solution. However, what is mentioned in the hint is not exactly correct. We cannot just simply conclude from this, just this, that R is equal to 1. It's not necessary. Precisely when n is, well, I need not say precisely, but that case is there. When n is even and R is minus 1, then also we get this equation is satisfied. So in general we can say this. R is equal to plus or minus 1. Let me also think about the other possibilities now, because you see, the nth, I just, you see, I am taking so much time here because I don't want to make a logical mistake and then somehow just have the solution without really understanding what is going on here. Instead, let's just take some time here and see exactly, okay, what about this conclusion? There are two possibilities, but are we getting it correctly? Is there any other possibility? Oh yes, this is how you can proceed to show. In fact, let me just show it in details. Exactly how we are getting that R is equal to plus or minus 1. This implies the absolute value of 1 is equal to the absolute value of R to the power n, or we can take the absolute value on both sides because they are the same thing. The left hand side is 1 and the right hand side, using the fact that absolute value is a multiplicative function, the absolute value of R to the power n. Okay, now we note one thing. R, of course, is any integer. See, there exist integers R and S. We haven't said anything else about R. R cannot be 0, because if R is 0, the right hand side is 0 but the left hand side is not. R may be negative, R may be positive, but now it does not matter because we have taken absolute value. So absolute value of R being non-zero has to be a positive integer, and that is why this is equal to 1, using that algebra trick where we can factorize this to the power n minus 1 algebraically. So from there we are getting this, which implies that R is either plus 1 or minus 1. So then substituting that back here, what do we get? Thus, A is equal to plus or minus D, since D divides B. D of course divides both A and B, being that they are GCD. D divides B. we have A divides B. Why? Because A is either plus D or minus D. If A is plus D, then you are directly having that A divides B. If A is minus D, then minus A divides B. But if minus A divides B, then so does plus A, it also divides B. So the ultimate conclusion we are getting. However, here there is a little problem with what is given in the hint. Okay, but that is not a problem for us because we have got the solution. So the solution ends here, and let me just end the video also here. I have noticed that if the video length is too much, I mean if it's too long, then you quickly lose interest because there is a certain sameness in this type of things. Now, to make things interesting, of course, I can just simply show some bits and parts of some areas of mathematics, but that ultimately serves no purpose. It may serve one purpose of motivating you that okay, it looks so interesting, then maybe I should study it, but that does not do anything more than that. Going through all the things like this may seem a little boring, but we have completeness, and most of all we have all the things. Okay, so these videos are going to be like this. The one thing that I can do to make things interesting is to make them somewhat short. So that's just it. So I'm ending things here itself tonight. If you want to say something, you can of course write in the comment section below, or you can mail me at my address, which will be there in the link will be there in the description. And this coming, so the next update will be on Friday, and that is again going to be our graph theory, where we have already seen some things on topological minors. We are going to see some more things. So with that, I wrap things up for tonight. So see you on Friday with graph theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.